let's get to the important part of this, which is why did we take a look at these accumulation functions? What's our connection? So what we want to do here is we want to plot the values of p on the graph of f, and then draw the curve for p to the best of our ability. Let's go back to our first example, and let's put p on this graph as well. All right. So we see that when x is -1, p is -1.5. So x is -1, and the function is -1/2, which means it starts right about there. And then the function p goes through the origin, and then it goes through the point over 1 up 2.5. So over 1 up 2.5 puts us right about there. And then it's over 2 and up 4.75. So 1, 2, 3, 4, and then we got to go off the graph a little bit. So it's maybe right around there is 4.75. And then 3 and 5.5, so that's going to be up here somewhere. And then finally over 4 and up 5, which will be somewhere in this vicinity. So if we were to graph this curve, because we do know that we've got some kind of curvature going on here, it does seem like we're looking at this situation. Okay. And believe it or not, there is some kind of connection between what we've just drawn here and the graph of f. We want to look at that a little more intently, but before we do so, let's go back to the second bullet point that says, let's do the exact same thing with the function for q on the graph of g. So we know that our first point was back 3, down 3.5. So we're going to go back 3 and down 1, 2, 3.5. We're going to go right into my old calculations. I apologize for that. And then back 2, down 1.5. So that's this point right here. And then back 1, and then no vertical movement. Over 0, up 0.5, which is right here. Over 1, up 0. Over 2, down 0.5. And then finally over 3, up 0. And if we draw this curve, we have something like this going on. All right, so this graph right here, this is the graph of q, and then up here we have the graph of p. Now, what, if any, connections can you find between the graphs of these pairs? Okay, well, let's look at the first one. Look at p for a second. What's going on with p? Describe it in your head. Did you say it's increasing for the start? Because it is. And then it decreases. It's negative. And then it's positive. It's concave up, it looks like, until right about there, and then it's concave down afterwards. All right. Let's go back to the first thing we said there. P is increasing, and then at the very end it's decreasing. Well, let's look at the graph of f. The graph of f is positive, and then at the very end it becomes negative. At the exact same point when P starts to decrease. Let's put that down for a second. All right. When P is increasing, that's when f is positive. And when P is decreasing, that's when f is negative. Does that same situation hold true for our second graph? Let's look at Q. Q increases, then decreases, then increases again. Whereas G is positive, then negative, at the exact same time that Q is decreasing, and then G becomes positive again, at the very end when Q starts to increase again. Increase, decrease, increase, positive, negative, positive. So P increasing, and then Q is also increasing when G is positive, and Q is also decreasing when G is negative. We know about this already. These are our connections between a function and its what? Yes, its derivative. These connections are true because these follow the derivative connections. Right? That's what's happening right here. This says the graph of g, but because we're taking the integral of g to get q, that means that g is actually the derivative of q. Because if you anti-derive the derivative, you're wiping the 2 out and you're left with the original function. So this says the graph of g, which is also the graph of q prime. Up here, p is the integral from 0 to x of f. Right? Which means that this graph of f right here is also could be considered the graph of p prime. That's the cool thing about these accumulation functions. Right? If you don't believe me, well, let's look at it a different way. We see there that p of x is equal to the integral from 0 to x of f of t dt. All right. Well, let's actually do this out. This means we have to take the antiderivative of f and then plug in x and 0. Well, we need to take the antiderivative of f. We don't really have a symbol for that that we know so far. So I'm going to do this. I'm going to make this capital F. All right, capital F is the antiderivative of little f. In other words, if we take the derivative of big F, we get little f. All right, and if we take the antiderivative of little f, we get big F. That's what's happening right here. We're taking the antiderivative of little f, we get big F of t dt. And that's being evaluated from 0 to x. Which one of these do we plug in first? Yeah, the x. So this is big F of x minus big F of 0. That's what p of x is equal to. But we want p prime of x. Well, when we derive this, we're going to take the derivative of big F of x. The derivative of big F is little f. And big F of 0, that's just a number. The derivative of any constant is 0. So the derivative of p is just f. That's why we can, another reason why we can write either f or p prime here. We can write g or q prime here. Here's the deal. We're doing the fundamental theorem of calculus all over again, which I'll explain some more in the next video.